we'll be discussing the week 0 assignment for the course ME125 aircraft propulsion. So the first question of the assignment is, a gas turbine engine operates on which of these thermodynamic cycles? So we know that the thermodynamic cycle that is used in a gas turbine engine or an aircraft engine is a Brayton cycle. So I'll discuss the Brayton cycle here. What happens in an aircraft engine is that we take the air from outside, that is the atmosphere, and we carry the fuel inside the aircraft. So the air is first taken in, it is compressed in the compressor, then in the combustion chamber the fuel is added where because of combustion the temperature of this air increases, and then finally that high pressure and high temperature gas is allowed to expand through the turbine. So this is the main process in an aircraft engine, and which is basically the Brayton cycle. So first we have an isentropic compression. So you can see in the PV diagram we have this isentropic line from 1 to 2, and in the TS diagram we have this 1 to 2 line which is at constant entropy, and then we have isobaric combustion, that is from 2 to 3. You can see it is a constant pressure line, and in the TS diagram the red lines which are drawn here are the isobaric lines. So again 2 to 3 indicates the isobaric combustion. In the PV diagram again 3 to 4 is the isentropic expansion process, which in the TS diagram is indicated by this constant line. So this is the Brayton cycle, which is the basic thermodynamic cycle which is used in aircraft engines or gas turbine engines. Okay, so the next question is, which engine from the following is not an air breathing engine? So as I said, an aircraft does not carry the oxidizer with itself because that will add on to more weight. So it just carries the fuel and it takes the oxygen in the air which is freely available. So that's why it's called an air breathing engine. And turbopropeller, turbofan and turbojet engines, all of these engines are examples of air breathing engine. However, a rocket engine does not depend on the air available in the atmosphere. So the answer is a rocket engine because it carries both the fuel and the oxidizer. And this is very obvious because after all, a rocket has to travel from the Earth's surface out into the space where of course air is not available, so much of oxygen is not available, so it has to carry the oxidizer with itself. So rocket is not an air breathing engine. Okay, so the next question is about an impulse turbine. The degree of reaction of an impulse turbine is what? So first of all, what is degree of reaction? What is an impulse turbine? So an impulse turbine is it is an example of a turbine. It is a very specific geometry of a turbine, and as I said earlier, turbine is a machinery which is used to expand the high temperature gases coming from the combustion chamber, right? So that is going to extract the energy from this high temperature high pressure gas, and it is going to give this energy back to the compressor. So that is the job of a turbine. Now what is the degree of reaction? That is very specific to the geometry of a turbine, and for an impulse turbine the answer is 0. So what we understand about the degree of reaction is that it defines how much workload does the rotor blade take and how much workload does the stator blade take. So blades of an impulse turbine are in the form of a bucket. So as you can see over here, if there is a jet of water coming and hitting these bucket shaped blades, they basically push the bucket shaped blades, and as a result the shaft of the turbines starts turning. So to the blade of the impulse turbine, you can see it basically turns the flow such that the axial direction, in the axial direction the velocity remains as it is, But if you just take the tangential direction, like if you see, the tangential direction of this arrow would be upwards, whereas the tangential direction of this arrow would be downwards. So the blades of an impulse turbine, they change the direction of the relative tangential velocity, and that is what leads to their degree of reaction being equal to 0. So we should remember this as a special case, that impulse turbine is where the workload on the rotor blades turns out to be 0. So the next question is, which velocity of the flow remains constant while flowing through an axial compressor? So the answer here is axial. Now the reason is that we'll see there are two broad classifications of compressors. One is the axial compressor and the other is called the centrifugal flow compressor. So in an axial compressor, the inlet flow is also in the axial direction and the outlet flow is also in the axial direction, and the flow basically goes through rotor stator blades, and one rotor stator together is known as a stage. The aim of the design of a axial compressor is to keep the axial velocity component approximately constant, and how a compressor achieves compression of air is by changing the tangential and relative velocity components. So it does not basically change the axial velocity component. Whereas in a centrifugal flow compressor, you can see that the inlet is in the axial direction and the outlet is in the radial direction. So it completely changes the flow direction. So these are the two broad types of compressors which are used in the industry. Next question is, with increase in operating pressure ratio, thermal efficiency of Brayton cycle, whether it increases or decreases or remains the same, what happens? So what is the operating pressure ratio? So for an aircraft engine, the pressure ratio across a compressor is defined as the operating pressure ratio. That is by design. And if we increase the compressor pressure ratio, how does the thermal efficiency change? So the answer is that it increases. So let us understand how. Now thermal efficiency is defined as the change in kinetic energy per unit of energy produced by burning of fuel, right? So here you can see that in the denominator we have m dot f into qr, that is the energy produced by burning the fuel coming in at a rate of m dot f, and delta ke is the change in kinetic energy. So basically how much more energy will I get in the air by giving a certain amount of energy through the fuel. So efficiency is always get by give. Okay, so here you can see that in the TS diagram I have drawn two cases. Case 1 is where we go from this red line, which is the ambient pressure line, to the green curve. Now this green curve basically demarcates the lower pressure ratio, lower operating pressure ratio, and the blue curve is the higher operating pressure ratio. So very clearly, if you need to achieve the same maximum temperature, then you need to do combustion you need to achieve the same maximum temperature, then you need to add more fuel over here. Whereas if the operating pressure ratio was much higher, then the amount of fuel you need to add in order to achieve the same maximum temperature is lesser. Hence, going back to the question, if we increase the operating pressure ratio, then the thermal efficiency of the Brayton cycle increases. So using this diagram, it's much easier to understand. Okay. Now the aircraft of which kind of engines fly at lower altitude? Now rocket is simply ruled out of the question because the rocket goes into space, so that's not an option here. Then if we see turbofan and turbojet, we find most of the commercial aircrafts operating at almost 36,000 feet, which is pretty high altitude. So the only option remains is turboprop. Now why do we find turboprop engines they cannot fly at higher altitudes? So the reason is, as you go to higher and higher altitudes, the density of air decreases, and a turboprop engine it gets its thrust from the mass influx. So the thrust equation depends on m dot, which is the rate of flow of the mass of air which is taken in by the aircraft engine. And the other important component that affects thrust is the exhaust velocity. Now turbofan and turbojet engines, they rely more on the exhaust velocity component. Turbofan relies on both m dot and the exhaust velocity, whereas turboprop, it heavily relies on the m dot component, that is how much mass influx we are taking. So as we go to higher altitude, since the density is decreasing, the mass influx also decreases, and hence that decreases the thrust of the turbopropeller engine. So it cannot fly at higher altitudes. Moving on to the next question, we have gas turbine engines have heat addition as a isobaric or isochoric or isentropic or isenthalpic process. So this we have discussed earlier in the diagrams, the PV and TS diagrams. So the answer is isobaric. So you can remember that 2 to 3 was the combustion process, which was at a constant pressure line, which is essentially an isobaric process. Okay. Next question. A converging area duct acts as a nozzle if the inlet flow is. So first of all, what is a nozzle? Nozzle is basically that component which increases the kinetic energy of the flow of the fluid going through it. So now what is the job of a nozzle? It is to increase the kinetic energy, and if we have a subsonic flow, then a converging area is needed to increase the kinetic energy. If we have a supersonic flow, then we need a diverging area to increase the kinetic energy. So that's why you will see that in turbojet engines which fly at around Mach 0.8, which is a subsonic regime, the nozzles are usually of the converging shape. So we do not have converging, diverging nozzles over there. However, if you see the nozzles of a rocket, they have both converging and diverging sections, because over there the first the exhaust flow is subsonic, the energy is increased, and the Mach number is increased beyond 1, and then we need a diverging section to further increase the Mach number, right? So here the answer is subsonic. Okay. The next question is, which of the following is a work producing machine? So as discussed earlier again, in an aircraft engine, a compressor is used to compress the air, that is decrease its kinetic energy and increase its pressure energy. But how do we even run the compressor in the first place? So that needs to be run through the energy that comes from the turbine. So turbine is the work producing machine. Remember always that nozzle and diffuser, they don't even have any rotating parts, so they cannot add work to the working fluid, which is air. So nozzle and diffuser are not an option. In compressor and turbine, turbine is the work producing machine, and the work produced by a turbine goes in running the compressor. So that's the answer. Okay. Next we have maximum temperature in the turbine inlet of a gas turbine power plant is restricted by what? So first of all, we need to understand that in a Brayton cycle, first we compress the air and then we increase its temperature through an isobaric combustion process. Now the higher I increase the temperature, the better, because if we expand the gas from very high temperatures to atmospheric temperature, then the amount of energy which is produced will be much higher. But remember that this very high temperature gas is going to go and impinge onto the turbine blades. It is also going to be faced by the combustor walls. So it is the material of the combustion chamber walls and it is the material of the turbine blades that matters. That is what restricts how much temperature you can actually achieve. So the answer here is material, and usually the limit on the maximum temperature is about 1400 Kelvin, after which the materials which are used in the combustion chamber may start melting. Now okay, one might use better material so that you can achieve higher temperatures and so on, But in any case, whatever be the material, it is indeed the material that restricts your maximum temperature in the turbine inlet. That's it. Thank you.